The topic of these tutorials is bitwise operators, otherwise known in the King textbook as low-level programming, simply because C allows us to get down to the bit level. Right. What we'll do is we'll start by talking a little bit about the number systems that we've commonly been using for programming. We work in a decimal number system. Right? Base 10 is what we're comfortable with. That's what we use for all our math. So when we mention number systems, when we mention a radix, that's the same thing as a base. So the radix of a decimal number system is base 10. And we see that there are 10 counting digits in a base 10 system, right? The digits 0 through 9. A base 2 number system is a binary system. There's two possible states or two counting numerals, 0 and 1. And the radix of that, of course, is 2, a base 2 or a binary number system. And when we're working with bits, we're going to be more concerned about this binary numeric representation. But what we do in C is we don't have a way of writing binary numbers. We have a way of writing hexadecimal numbers. And so that's a base 16 number system. And of course, there's 16 counting numerals in that, 0 through 9. And then we count A, B, C, D, E, F in that hexadecimal or base 16 number system. Right. All of our numbers are based on positional notation. Right. We use positional notation without even thinking about it. So in our decimal number system, if I were to write the quantity here, 456, we would interpret that as 456. We could write that as 400 plus 50 plus 6. But when you think about this, we use positional notation. We use powers of 10, right? 10 is the base. And so we could write the number 456 as 4 times 10 squared plus 5 times 10 to the first plus 6 times 10 to the 0. Right, and when we look at 456, we know that the 4 is in the hundreds position, which is 10 squared, right? 10 raised to the power of 2. We know that the 5 is in the tens position, which is 10 to the first, and the 6 is in the ones position, and 10 to the 0 is the ones position, right? And so we use the same positional notation to represent other number systems. Right? For binary numbers, we use binary digits or bits, right? And those binary numbers appear to us to be strings of zeros and ones. And the magnitude, if we want to convert it to another number system, is determined by the bit position. So here, what I've labeled as bit B0 is our least significant bit. And these move up by powers, but 2 raised. So powers that are increasing, so power of 0, power of 1, power of 2, and it's 2 raised to that power, right? So 2 to the 0 power is the ones. 2 to the first are the 2s. 2 squared, 4. 2 cubed, 8. 2 to the 4th, 16, and so on. All right, so this is an example of an 8-bit binary representation. We have 8 different bit positions. B0, least significant, B7, most significant, right? Our most significant bits have a greater weight because they're 2 raised to a larger exponent. So if we look at this binary representation, this is 00100101. This binary number has a base 10 magnitude of, well, we take everywhere there's a 1 in B5 or in the 2 to the 5th position. We write that as 1 times 2 to the 5th plus 1 times 2 squared plus 1 times 2 to the 0, which is equal to 32 plus 4 plus 1, or 37 in a base 10 number system. So we can convert that binary number using the positional notation back to our decimal base to a number that makes more sense to us. Right. So to remind you then of the counting numbers, in decimal, here we show that we're counting from 0 to 15. In binary, to count from that same 0 to 15, we need 4 bits to represent the number 15. So I've shown a binary representation here, a 4-bit representation of the decimal number 0 is 0000 in binary, and you can see the other numbers here as well. And in hexadecimal, the same representation then goes from 0 through F. Right. What we're going to see in C, we're going to write numbers in hexadecimal notation, but when we get down to the bit level, we're going to have to understand binary. And the nice thing about hexadecimal and binary is that hex is base 16. Well, 16 is 2 to the 4th. So 4 bits are needed to represent 1 hexadecimal digit. Right, so we'll be able to transfer back and forth between hex and binary simply by converting a hexadecimal E to a binary 1110. Or if we had a binary 0100, we'd know that's a hexadecimal 4. Right, so we group everything in 4s and to convert. Here's another example here. Every 4 bits right, as a hexadecimal value. So if you have this binary string here, you want to convert it to hex, we start with the rightmost bit, the least significant bit, and we form a group of 4. That's what I've done here, separated by space in the middle to allow you to read that easier. We have these two groups, so 0, 1, 0, 0 is 4, 1, 1, 0, 0 is C. So the hexadecimal representation of this binary number is C4. Now in C, we write 0x to indicate that this is a hex constant. So in a C program, we'd have to prepend 0x in front of this to let the C program know that we're writing in base 16. Right. Hexadecimal to binary, well, we take the hexadecimal digits here. So this is hex 3, 5. And a 3, the 4-bit representation of a 3 is 0, 0, 1, 1. And the 4-bit binary representation of the number 5 is 0, 1, 0, 1. So it's very easy to convert back and forth from hex to binary and binary to hex. And we'll make use of that. So the different bitwise operators we'll be using, we'll use some terms first, once again, to remind you that a bit stands for a binary digit. It can have 2 values, 0 or 1. In Boolean algebra, those are often interpreted as true or false. Right? There's another term you'll hear quite often called a nibble. Well, a nibble is simply 4 bits. A nibble is half a byte, 4 bits. We know those 4 bits have 16 possible binary values. 2 to the 4th equals 16. And remember, 4 bits are the ratio of 1 nibble to 1 hexadecimal character. So we use 4 bits to convert those 4 binary digits to 1 hexadecimal character and vice versa. Other common terms are a byte. Typically, there's 8 bits in a byte, or a byte is made up with 2 nibbles. A word is 16 bits, and a double word is 32 bits. We won't use these very commonly, word or double word, in this class. We'll be more concerned about how many bits there are in a byte. So different bitwise operations we can use will be able to allow us to manipulate individual bits stored in a number. That comes in handy in embedded programming. We're always concerned about the amount of space our program takes up. Well, instead of using a whole 8-bit value to represent something, we're going to use each one of the individual bits to store a value. Right? You'll often see this in status registers. Hardware registers will store certain flags that we can query. A lot of times with embedded programming, we're going to need to set a bit to 1. We're going to need to clear it to 0. We might need to read its status. And we can use that then, these bitwise operations we're about to learn, to convey different information. Right? So the different operators are listed in this table here. They operate on integer data, right? We don't use them on floating point data. We use them on integer data, right? Signed or unsigned. And so this symbol that looks like 2 less than symbols is the left shift operator. This one that looks like 2 greater than symbols is the right shift operator. There's no space in between these. The tilde is the bitwise complement. The ampersand will be used as bitwise and. The caret here is the bitwise exclusive OR. And the vertical bar, vertical pipe, is the bitwise inclusive OR. So let's go ahead and take a look at the truth tables for these operations. Oh, sorry, before that, here's the precedence table. Right. We can see that the left shift and the right shift operators are lower in precedence than these math operators, plus and minus. Right. The AND operator, the XOR, right? AND is higher than XOR. XOR is higher than OR. Right, these are bitwise operators. So you can see then where their precedence in. These are logical operators down here, logical AND, logical OR, are different than the bitwise operators. Right. Let's take a look at the bitwise AND operator. Right. We already know the truth table for an AND gate. Right. If you've taken a logic design course. If not, we have 2 inputs for this AND truth table, X and Y. And here are the 4 unique binary combinations for X and Y. We'll see then when we take this value of X, 0, and we AND it with this value of Y. So X ANDed with Y, the output of 0 ANDed with 0 always gives us a 0. And we'll see that with an AND gate, whenever any one of the inputs, here 0 ANDed with 1 produces a 0. 1 ANDed with 0 produces a 0. What I was about to say was that when any of the inputs is a 0, the output is a 0. The only time the output of an AND relationship is a 1 is when all of the inputs are 1. So 1 ANDed with 1 produces a 1. And it's important then that we also understand these Boolean algebra axioms. So x ANDed with 1 will always produce x. And let's take a look at this. X has two possible values. If we let x equal 0, we can see that 0 ANDed with 1 produces 0. And when we let x equals 1, 1 ANDed with 1 produces 1. So in both cases, we AND x with 1 and we get x back. So thus x ANDed with 1 is x. The other important axiom is that x ANDed with 0 always produces 0. So let's look at the two cases. When x is 0, we see that 0 ANDed with 0 produces 0. And when x is 1, 1 ANDed with 0 produces 0. Thus, x ANDed with 0 equals 0. So these axioms will be important in our usage of bit masking later. Right. So let's take a look then at how this bitwise AND operator, the single ampersand, works on two different values. So we're going to assume that x and y are both 8-bit inputs. So both x and y are 8-bit numbers. We're going to assign the decimal value of 17 to x and the decimal value of 9 to y. And we want to find the result of x ANDed with y. In order to do that, we want to convert 17 to its 8-bit binary representation. We'll convert 9 to its 8-bit binary representation, and then we'll AND the individual bit pairs of x and y to find that x ANDed with y. Right. So here we're converting 17 to its 8-bit binary representation. Well, 17 right, is the same as 16 plus 1, and that's 1 times 2 to the 4th plus 1 times 2 to the 0. So here's the binary, the 8-bit representation of 17. Similarly for 9, we want to convert 9. Then 9 is simply a plus 1, which is 1 times 2 cubed plus 1 times 2 to the 0. Here's the binary, the 8-bit binary representation of the number 9. Now that we have these binary representations for these values, what we do is we're going to AND them together. So what I've done down here is I'm showing the bit positions B7 through B0. So here's the binary representation of x. Here's the binary representation of y. And when they're ANDed together, these bit pairs are ANDed together. So the pair at B0, this 1 is ANDed with this 1 to produce a 1. Then this pair is ANDed together. So 0 is ANDed with 0, produces a 0. The bit pair of B2 is ANDed, 0 is ANDed with 0, produces 0. The bit pair here representing bit position B3, 0 ANDed with 1 produces a 0, and so on. So now you can see that the final result of x ANDed with y is this binary number. And if we were to translate that back to decimal, that's actually a decimal 1. So bitwise operators, a bitwise AND, you need to remember that these operations happen individually with each of these bit pairs, right, to produce then the result. Similarly, with the OR operator, the OR operator is the single vertical pipe. That's the bitwise OR. And so the OR truth table, we'll see that whenever any of the inputs to an OR, bitwise OR, are 1, it will produce an output of 1. All of the inputs must be 0, so 0 ORed with 0 produces a 0. Otherwise, in these other three combinations, we always have one of the inputs is a 1, it produces an output of 1. And the important Boolean algebra axioms for OR gates, to remember, x ORed with 1 produces 1, x ORed with 0 equals x. And here's the proof for each of these. We can see that when we let x equal 0, 0 ORed with 1 still produces a 1. When x is 1, 1 ORed with 1 is still equal 1. So thus we've shown that x ORed with 1 is equal to 1. And now for this axiom, when x is 0, well, 0 ORed with 0 gives me a 0. When x is 1, 1 ORed with 0 gives me a 1. Thus we've proven that x ORed with 0 still returns x. We'll see later where we use these and why they're important. Let's take a look now if we say x ORed with y. Again, we're going to use the same values of x and y. So x is going to be decimal 17. Here's its binary representation. Y is decimal value 9. Here's its binary representation. Same as the x ANDed with y. And I need to correct that slide because we are not ANDing, we are ORing. So copy paste got me into a little bit of trouble here. All right. So we're going to find the result of x ORed with y. So, and I don't want to AND them, I want to OR the individual bit pairs. So once again, here's X, here's Y. We OR the bit pairs together. So we go to position B0, 1 ORed with 1 gives us a 1. In B1, 0 ORed with 0 gives us a 0. In B2, 0 ORed with 0 gives us a 0. B3, 1 ORed with 0 gives us a 1. And so on. We OR each of these bit pairs together to produce this final result. And this is actually then a decimal 25. This binary representation is 16 plus 8 plus 1, or decimal 25. The XOR, or the exclusive OR operator, the bitwise exclusive OR, is this caret. Its truth table is X ORed with, when X is exclusively ORed with Y. So 0 exclusively ORed with 0 produces a 0. 0 exclusively ORed with 1 produces a 1. 1 exclusively ORed with 0 produces a 1. 1 exclusively ORed with 1 produces a 0. The XOR gate gives you zeros when you have an even number of ones for inputs. When you have an odd number of ones for inputs, then you produce ones. Right? So here, X and Y are different. X and Y are different. They produce ones. Here, X and Y are the same. An even number of ones. Well, there's 0 ones. This produces a 0. Right? An even number of ones. 1 exclusively OR with 1 produces a 0 because there are 2 ones. Right? So the XOR gate is also known as the odd gate, because you always get a value of 1 whenever there are an odd number of ones in the input. Important Boolean axiom with this is that when you exclusively OR 1 with X, you get not X. Oh, it works as a toggle. Right? So we can see here when X is equal to 0, 0 exclusively ORed with 1 gives us a 1. When X is equal to 1, 1 exclusively ORed with 1 gives us a 0. So we actually then end up toggling or complementing that bit. X exclusively ORed with 0 produces X. Right? So when X equals 0, 0 exclusively ORed with 0 gives us 0. When X equals 1, 1 exclusively ORed with 0 gives us 1. So X exclusively ORed with 0 gives us X. Right? Those are a couple of important Boolean axioms that you'll need to know. Now, we're going to use the same values in this example for X and Y, 17 and 9. And when we exclusively OR them together, once again, we're going to do so with bitwise pairs. And I apologize again. I did a copy paste earlier when I made these slides. And I was not thorough in my update, was I? All right. So that should be exclusively OR. So we exclusively OR, these are bitwise operators. So bitwise operators means we work bit pair by bit pair. So 1 exclusively ORed with 1 produces a 0. 0 exclusively ORed with 0 produces a 0. 0 XOR 0, 0 produces a 0. 0 XOR 1 produces a 1. 1 XOR 0 produces a 1. We end up then with this as a value of X exclusively ORed with Y. And that happens to be a decimal 24. That's 16, 2 to the 4th, plus 2 cubed. 16 plus 8 is 24. Right, so that's the result then of X exclusively ORed with Y when they happen to have these two values. All right, that lets you know then how these bitwise operators work. We have one final bitwise operator, the complement operator. So the complement simply gives you the inverse. So there's always a single input, X. X can take on two values, 0 or 1. Well, the complement then of 0 is 1. The complement of 1 is 0. Right? And the tilde then is our bitwise operator. Right? Let's take a look at what happens when X is the decimal value 17. What is the value of not X? So complement X is often referred to as not X. And this is also a bitwise operation. So here then is the binary value for 17. And then when we invert each of the bits, each of the bits is individually inverted, right? So the inverse of 1 is 0, inverse of 0 is 1, inverse of 0 is 1, inverse of 0 is 1, inverse of 1 is 0, inverse of these zeros is all 1. And so while X is 17, not X happens to be 238. So like I said, it's important to remember that this tilde works on each individual bit. Right. And then I provided you with some programming examples along with these lecture slides. So let's take a look at example 1. Right. Here's example 1 in code blocks. We're just going to display the following results of the bitwise operations. So these are the same numbers we just looked at in the slides. I've made X an unsigned char. It should be 8 bits. Right. Set it equal to 17, and then Y is equal to 9. Right, we're going to print a couple of blank lines, and then we're just going to show the results of, we're going to show the values of X and Y, and the results of X ANDed with Y. So you can see here in this printf, right, X will be substituted in here for %U. So I'm using %U here for this unsigned char, right, and a field width of 2. Y will be substituted in here, right, this argument here, and then the value of X ANDed with Y will be substituted in here as the result. So let's build and run this. Right, so we can see that 17 ANDed with 9 produces a decimal 1. 17 ORed with 9, 25. 17 exclusively ORed with 9 gives us 28. And then not 17 gives us 238. And here I've done something different. So notice I've got this HHU. Well, on my system, if we run this with %3U, when we say not X, let's build and run. Look at the huge output I get here. I actually get what looks like a 32-bit output. So there are specifiers, right? There are link specifiers that you can use. So if I say HU, H is, so if U is an int, HU is half an int or a short. So if I now build and run that, notice then I get 65,518. I get a smaller decimal representation, right? And if I want an 8-bit representation of this, I say HHU. So half of an int is actually a byte or a char. So if I build and run that, then I get 238. So this just happens to be a little quirk here of C when I'm showing this value of not X in order to just show that 238, whittle that down to the 8-bit representation. I had to do this. Using this length specifier here with this. Now, I might have been able to cast this. So if I were to cast this and get rid of the HHU and just have the U, let's build and run. Notice I get the 238. That tells us then when we just say, even though I said X was an unsigned char, when I use this bitwise operator with it, and I just use the %3U, we get this strange, well, we get this 32-bit output that we didn't want. The one way to get rid of that is to specifically cast this result then to the unsigned char, or to use this link specifier that says just give me half of an int, which is a char or a byte. Right? So some little quirks here with C, actually with printf and the way it's displaying this information, because we didn't have to do that with these operations here. Right, but for this particular one, we had to do that. All right, so moral of the story is whenever you're getting strange output with printf, you might want to think about the length of your data type, use the appropriate link specifiers, either that or cast the result. All right, let's take a look at example 2 now. So example 1 gave us the results of then, it gave us decimal results, right? Our output was decimal. I'm going to do the same thing in example 2, but we're going to show the output as hexadecimal. So hexadecimal, then, we use %x, right? Here I'm saying I want to field width of 2, and the pound flag says to go ahead and show the preceding x to indicate that this is a hex result. So let's just go ahead, let me add this to the project, let me remove the other one, and let's build and run this so we can see the hexadecimal output. So here's our hexadecimal output then, right? Which makes a little more sense to us than simply, and I'm showing then as well the hexadecimal representation of these values, right? It makes a little more sense then to actually show, oh, sorry, wrong example. All right, right output, wrong example. All right, so it makes a little bit more sense to show the hexadecimal values of X and Y and then where their result is, because we can actually then translate to binary very quickly and check the bit operations. The decimal results are an extra step for us. All right, and we'll see that when we work with bitwise operators, we often are going to work with hexadecimal representation. All right, and now example 3, I want to show you the difference between a logical and a bitwise not. So this slide here then warns you about the difference between bitwise and logical, right? So logical is this not operator with the exclamation mark. Let's pop up code blocks. Let's look at example 3. So now that I've added that into the project, I've set X equal to 1. And we'll see that when we say not X, right? So here when we say not X, remember this logical operator simply gives us a true or false, a 0 or a 1, right? We'll see then if not 1, we're going to get a 0. But when we use the bitwise operator with X, when we say not 1, well, let's show you what we get. And that's what I wanted. We clean that, build and run. All right, so we can see that the difference between the logical not, so this not X gives us a 0, because X is a 1, not 1 is a 0. But tilde X, the bitwise operator, right, inverts. So our 1 here is all preceded by 0. So all of those zeros are inverted to 1s. This lone 1 out here in the least significant bit position is inverted to a 0, so we get this hex FE, right? So you need to be aware of the fact that when you use the tilde, there's a difference that inverts every individual bit. Here, this just looks at the whole number and says, well, if this number is any non-zero number, not a non-zero number or not true is false. And if this is 0, then not 0 gives you a 1. So know the difference between the two and use them appropriately. All right. All right. In the next lecture section, we'll take a look at the bit shift operators. That will be in part 2.